They say life is stranger than fiction.
With your ruler, put some charges on it with your jumper, and then run your tap. And then if you put the rod close to the tap, have a look at what happens to the water, how that moves, and that can tell you a little bit about what's going on there.
But sometimes what we see in movies or read in books is so incredible that it obviously couldn't be possible. Or could it?
And so you end up with this magnetic kind of dipole within the diamagnetic material, which in this case is a frog. So depending on how strong your original magnet is, you can actually, the magnetic repulsion between the frog and the actual magnet can be so strong that it can overcome the effects of gravity. So you end up pushing the frog up and the frog will float.
Welcome to Sci-Fi Sci-Fact. I'm Brian Crump, and this is a podcast where we take science fiction's strangest ideas, weirdest elements, most unfeasible plot drivers, and explore if they could actually happen in real life. Maybe they already have. And in every episode, we bring in a scientist from New Zealand's MacDiarmid Institute to explain the theories behind some of fiction's more fantastic flights of fancy.
Hello?
I wondered when I'd be seeing you, Mr. Potter. Seems only yesterday that your mother and father were in here buying their first wands. Ah. Here we are. Give it a wave.
Well, it's another bit of a sci-fantasy sci-fact, really, because it's the magic wand, the science behind the magic wand. You know, the one that the apprentice gets hold of from the sorcerer and, points it at the brooms and the brooms start doing their work, but then, hey presto, he can't stop it. Or other stories to do with magic wands. And here to talk about that science, whether it's possible that a wand could exist in real life, as well as in stories, is Dr. Natalie Plank, MacDiarmid Institute Principal Investigator and Senior Lecturer in Physics at Victoria University of Wellington. Kia ora, Natalie. Welcome back to Sci-Fi Sci-Fact.
Kia ora, Brian. Thanks a lot for having me on the show again.
Oh, it's lovely to have you on. Now, what does Wiki say about the magic wand?
I had a bit of a look on Wikipedia about magic wands, and I had no idea that there were so many stories about magic wands going back in time. Quite an ancient concept, actually, whereas I'd always just sort of been thinking about, as you say, the Sorcerer's Apprentice and things like fairies with their magic wands, and Harry Potter, of course, being a famous wand wielder. So yeah, that's kind of cool, isn't it? But a little bit out with our real life daily experiences.
How far back? I mean, I'm looking here, maybe almost 2,000 years, if I'm looking at the same wiki page that you looked at.
Yeah, I think so. And I was really surprised, right? Because it wasn't just in literature and things. It was actually real artifacts found with actual people and things. And so, I don't think people in the past actually had the magical capabilities to levitate things with their magic wands and stuff like that. But it is really kind of a cool concept, and it's something that kind of magic behind making things move without touching them, I think is really exciting to people.
There are a couple of things that come to mind, Natalie. One is that the magic wand is also a big part of the magician's craft. And isn't it? And I'm wondering whether that's because this tells us that magicians have been doing magic tricks for over 2,000 years.
Yes, that's a very good point. I was recently at a magician's show at a birthday party, and it's pretty impressive what they can do, actually. But I do not think they're kind of getting around the laws of physics. And that's kind of the cool thing, that physics is actually really magic.
Right.
But for physicists, right, a bit of a kind of thing that you don't really think about as a non-physicist, perhaps, is that we're constantly thinking about that concept of action at a distance, like things happening when objects don't actually touch. So, a big thing that we can think about is the concept of gravity, right? That the heavenly bodies are kind of all held together in their orbits and stuff like that. And there's a gravitational force from the sun that's attracting the Earth. And we're kind of quite comfortable with that, but that's something which is happening on the really kind of massive scale.
And in some ways, just as important, maybe, okay, the sun, without the sun, we wouldn't be here. We wouldn't be having this discussion. But not far behind is the gravity that holds the Earth together, that holds us to the Earth. There you go. That was an example of it in action. What are these?
Exactly.
I think these are a beer mug. But beer, these things, they look like the kind of stuff you put a beer glass in. What are they doing in the studio? I'll blame Matinee Idol for that.
And we can drop our apple, right, and see that it will fall from the table and land on the ground. And that seems quite real to us because we can see it and we can say, okay, that's what's happening. But there's also lots of other interactions between things. And if you start to look at kind of electromagnetic effects, so that's where you've got charged objects. So say in an atom, you'll have a electron and you'll have the positive particle in a nucleus. So both of those things experience electrostatic forces. And what's interesting about electrostatic force compared to, say, the gravitational force is that it can be in the direction of attraction and repulsion, whereas gravity is always attractive, right? So this is a little bit different. And it's that thing of the repulsion is where you can start to actually see things in real life, like actually with your eyes, you can see it as well. So I think most of us have played around with magnets as kids and what have you. So yeah, we can't do magic ourselves. And unfortunately, I can't wave my wand and clean the kitchen and have the dishes wash themselves, which would be really good, right? But unfortunately, although I'm talented at physics, I'm not talented at that. But yeah, we want to kind of think about why things move when we can't see the interaction. And so the other day, my kids were at a party at Space Place, and they came home with these magnets, and they're two, quite strong magnets that interact with each other. And the 3-year-old was just captivated by the fact that he could make one of them move without touching with the other one. And, he was actually just standing there sort of waving it around like you would a magic wand and making this other magnet spin around and things like that. So it's something that even children really get behind, that kind of wonder of how that works and what it looks like. So there are a few things that you can do to make a magic wand in your home. Is
it possible, Natalie, that thousands of years ago, some people got some kind of metal rod and it was magnetized, and that was maybe one of the original wands? People, my goodness, it moves this other thing that's metallic. They might not have used those words, but wow, that's magic. That's a wand.
Yeah, it could be that things that people observed appeared mysterious when they didn't know the whole story behind magnetism. So you could do this at home. You could get a ruler, just a plastic ruler, like you would use in school, one of those 12-inch, 30 centimetre long rulers. Yep. Try getting a few different fabrics. So you could get whatever you've got around in your house, maybe a woolen blanket or something like that. And if you rub those two things together, charges will move from one material onto the other. So it doesn't really matter which type of charge it is, if it's positive or negative. You'll end up with a net excess or deficit on one of these materials just from that charge transfer. So you could take, say, any kind of drinks can that you've got, empty Coke can, beer can, whatever, and pop it on your table, charge up your ruler, and then just point it close to the can, but don't touch it. And you'll see the can move without you touching it. Because when you bring that charged object close to the metal, all of the charges on the metal will kind of move so that the like charges move away from if you've got two negative charges, they'll move away from each other. And you'll end up with a net positive charge closer to the ruler than the other end, and that will then kind of pull the can towards you, and it will roll towards you.
Is that magnetism, Natalie, or is that static electricity? And are they different? Are they the same thing?
No, they're not exactly the same thing. So magnetism is something that happens when charges move. So, if you put on, if you have a compass, so a compass for finding your direction in the world, so pointing north, and you have that next to an electrical wire and you turn the wire on, if you start having a current, that compass will deflect because there'll be a little magnetic field created from that wire when the charges move. And so these were things which people were working out in the late 1800s or so with Michael Faraday and people like this around magnetism and that relationship between moving charges and things becoming magnetic. And that's really like what's going on inside materials. Things like iron, that has a permanent magnetic behavior, and other materials like that they've got these magnetic domains which have all lined up. So all of the magnetic points are all facing in the same direction, more or less, in these domains. And so that's why they're magnetic. And that comes down to what's going on at the atomic scale. Where are the electrons and how are they behaving in the material? And that's pretty difficult to explain all of that. You have to go into some quite advanced quantum mechanics.
Natalie, you talked about a plastic ruler. And one of the things that interests me about static electricity is it seems that it's often things that aren't normally associated with conduction of electricity that work well when you want to build up a static charge, something that's plastic. Or, the other thing is to rub a balloon and then hold the balloon over your head and watch your hair lift up. Now, a balloon, again, is made of what? Rubber or rubber plasticky kind of substance. Sorry for being not particularly scientific about that description. Plastic ruler, these things normally don't conduct. Why is it that they then build up a static electric charge?
I think it's because they can't conduct. So there's nowhere for that charge to go. So it builds up. So it's sort of just there. Whereas it can go through you, like when you're on a slide or something like that. And, you build up static charge and then you touch your friend and then you get that shock when the charges move
I know. And that could be quite vicious. Especially, and here's another thing, Natalie. Why did that tend to happen when the weather was dry? When there was a big anticyclone around, why was it more likely then I get a zap off the playground slide?
Because the water and the air can kind of move those charges away. If you've got humidity in the air, you can't build up the same level of charge. And so that's like a really good demonstration with the Van de Graaff generator. That's basically sort of rubbing things and moving charges onto a surface. So you hold that top surface of the Van de Graaff and the charges move all over your body. And then they make your hair stick up on end, which is quite a good fun demonstration.
The Van de Graaff, that's what it looks a bit like, a sphere, and it's metallic, and you touch it, but you've got to be insulated from the ground. And I was too scared. But I watched other people's hair go up in the fifth form science class.
No, I was a bit scared of that too, actually, to be honest, which I probably, shouldn't really be. But it's good fun, right? But you're right, like we've got lots of everyday experiences of that, the slide and things like, if you've got a hole puncher and then all those bits of paper, those little circles of paper, and if you drop them, they get stuck everywhere, right? And they're really difficult to pick up. They get stuck to your hands, what have you. That's all electrostatics. So electrostatics is really a kind of action at a distance phenomenon, and so is magnetism.
I just want to clarify. So what is going on, say, when we rub a ruler? I know you kind of explained it, or go down a slide. Are we leaving electrons behind on the slide as we rub the slide, as we fall down, or is it leaving electrons on us as we go down?
It depends on the material, actually, what transfers which way. So, you'll have positive charges moving or negative charges kind of coming from one material to the other, depending on exactly what it is. So, there's an excess of charge being left behind or put on.
Does it matter which? If we have an excess of electrons, does that mean we're on the slide? Does that mean there's going to be a discharge of electricity when we touch the ground?
Yeah, or when we touch our friend,
Right.
they'll want to move quickly.
If we'd left
off.
behind electrons on the slide, would we not get a zap?
Actually, maybe we would from the other person still. So yeah, I've never actually really thought about this so
because
in depth, because then they would have an excess relative to you, perhaps, from what they're doing. So yeah, I'm
but
not sure.
maybe if they were already grounded, that wouldn't matter. And once we were grounded,
once we were all grounded, yeah, we'd all be happy again.
But if we weren't, our friend could still zap us before we stepped off the slide.
Yeah, and there's it's kind of a fun thing to do, but not very kind.
Natalie, you've done this, haven't you?
The charges zap you somehow. But yeah, that electrostatic charge is very strong, right? It's a lot stronger than the gravitational charge for things. If you were to compare like for like, this, the mass charge of gravitation, the gravitational pull of these small charges compared to the electrostatic force. But we don't see it so much in our everyday because most things are electrically neutral, right? We've not typically got as many positive charges as negative charges. So we don't go about really being en masse attracted to things from electrostatics.
But lightning is electrostatic discharge, isn't it?
Yeah, it is.
And that is incredibly powerful.
Very powerful, yeah. And yeah, loud and scary and everything, but amazing and beautiful as well. But yeah, electrostatics kind of give you one side of the story, but there's also a lot of cool things with magnetism. So again, like magnetism is very linked to the electrical charge effects. So that's why we study electromagnetism as a subject together. And they're so intricately linked, like the origin of the magnetic field coming from these moving charges. And there's a very famous demonstration of the levitating frog. I don't know if you read up about that at all.
I've heard about frogs moving because, you stuck some kind of electric charge into them and their legs moved, but not this, not levitation.
Oh, this is different. So this is the frogs do not get hurt by this, but the frogs are what we call diamagnetic. So again, this is kind of a complicated phenomenon, but iron is what we call ferromagnetic, so that's always magnetic. But some things only kind of exhibit some weak magnetic effects in the presence of a magnetic field. And frogs are one of those things. So water is one of those things. What happens is that you apply the magnetic field, and it's actually a very small effect, but you've got the electrons, whizzing around in the atoms and molecules in the frog around their nucleus. So you've got a moving charge, and these are in the presence of a magnetic field. And at some point when it's going around in one direction, say, the electron moving induces its own magnetic field. So that moving charge on the electron has a counter magnetic field to the magnetic field that you've applied. And some of the electrons move faster, some of them move slower. So the effect doesn't quite cancel out. And so you end up with this magnetic kind of dipole within the diamagnetic material, which in this case is a frog. So depending on how strong your original magnet is, you can actually, the magnetic repulsion between the frog and the actual magnet can be so strong that it can overcome the effects of gravity. So you end up pushing the frog up and the frog will float.
Is there any evidence that this has been an evolutionary device for frogs to help them survive?
Well, it could be all kinds of things. You could probably do it with a mouse if you had a big enough magnet. You could maybe do it with a person. So it's not really evolutionary as such, but I think they chose frogs because frogs are kind of cute, and people don't worry about frogs that much.
I hope the frogs. You certain the frogs didn't suffer? They're not feeling uncomfortable when they're levitating there in this magnetic dipole.
I wouldn't have thought so. I think the frog would be fine. And, so it just kind of floats like it's in microgravity kind of thing, like what you would do on the space station or something like that without anything really happening to it. But you need a really strong magnet to do this. So it's not something that you're just going to have hanging around in your living room. something like that. But you can see that kind of same effect as well with superconductors, and when you have you can levitate magnets over superconductors, because the superconductor will try and push out any magnetic field that comes around it, and it will create its own magnetic field repulsing the magnet above it, and you can see floating magnets, which is quite a cool physics demonstration that many people could have seen even in, you know, school classroom and things like that. It's a really fun thing to do, but it is really, you know, things can float. How you would get that kind of powerful magnet into a wand?
Yes, that's the thing. I'm wondering, how could you do this with a stick?
That is a lot harder to do with a stick. So, you know, obviously magnetic fields do extend into space, but it's tricky. It's more sort of done in a tube rather than...
It seems to me, Natalie, that it's more likely that the real-life equivalent to a wand would be something that dispenses static charge. Would you agree?
Yeah, that's something that more feels like a wand. And I've got another good demonstration for people to do at home, again with your ruler or any other kind of rod or thing that you can find. Put some charges on it with your jumper, and then run your tap at home. And then if you put the rod close to the tap, have a look, the kind of flow of water. Have a look at what happens to the water, how that moves, and that can tell you a little bit about what's going on there. It's quite good fun. It will deflect.
All right, yeah.
So there's lots of science you can do at home. So if anybody is self-isolating, they can entertain themselves with a few of these simple...
All you need is a plastic ruler and a tap, or something to rub it against. Well, rubbing it against your body, what things should you rub a plastic ruler against to really maximise the charge building up?
I think wool works the best, I think, in my experience. I think in some of the old textbooks, though, there's some pretty dodgy descriptions on different materials like cat fur and stuff like this. And I don't think you probably don't want to chase your poor cat around the house trying to rub.
They sometimes like to rub up against things, but maybe not rulers.
Maybe not, no.
We're talking about the science behind, or the possible science behind, the magic wand with Dr. Natalie Plank, MacDiarmid Institute Principal Investigator. She's also a senior lecturer in physics at Victoria University of Wellington. Do you think, Natalie, that you could have a wand that builds up a static charge that's sufficient to really do some quite serious discharging without the person holding it getting zapped themselves? Because they would have to be earthed, or they would have to be insulated from the ground. Otherwise, they're going to zap themselves with the wand, aren't they?
Yeah, you probably want to be careful. But yeah, there's a limit to how much you can manually sort of charge yourself up, I guess, without the use of some kind of machine.
And I guess the other thing is, once you've dispensed the charge once, that's it. You then have to charge it up again. So you're going to have a lot of wool around, right?
Yes, you're not really going to have the element of surprise as well.
What about more modern technology that could do the same sort of stuff in a stick? I'm thinking of lasers of some sort.
Oh, so you're thinking of kind of the laser tractor beam type situation.
Yeah, maybe.
Yeah, that's something I probably know a bit less about in general, but I think that's the whole idea of an optical tweezer, where you have a very well-focused laser beam, and you might be trying to move something and kind of trap it in a location or move things around. It could be, something like a cell or something like that you want to look at. And again, light is another electromagnetic effect. But there, I think they're using the kind of energy and the push from the light as a photon, that kind of particle of light, sort of coming along and pushing the atom into the focal point of the laser beam.
I guess
and they get trapped.
The crucial thing is it's not mechanical. Somebody isn't grabbing the atom with any kind of tiny pair of pliers or calipers or anything like that, or tweezers. They are using light, photons, to move these very, very small objects around.
Yeah, it's incredible, really, when you think about it, that, light can actually be, targeted and strong enough to move things.
Natalie, now probably the main use of a wand for a magician is to distract us, right? They wave the wand and we look at the wand moving and we don't see the other hand that's not holding the wand doing the little sleight of hand. But in your little study of the magic wand, do you think that there are any maybe real-life applications where the stuff we've been talking about actually was what that stick was doing?
I'm not so sure. No, I don't think so. I think the sleight of hand, but I'm not an expert on the history of magic. Just I'm not sure. Have you come across anything that you think?
Well, what's our understanding of the discovery of magnetism, even an accidental discovery? And that's something I was going to actually ask you, Natalie. How do you make a magnet in the first place?
Well, how you make a magnet, that's comes down to the material properties of what it is that you're making the magnet out of. So things like iron, which are inherently magnetic because of how those atoms behave. I guess magnetism probably was sort of discovered way back in ancient times. I can't remember the full details properly, but there will be regions of the world where people notice strange effects happening, things that had happened after thunderstorms or different types of rock that would attract things and stuff like that, going back, really a long, long time ago. And a lot of these words like magnetism probably derive from the ancient Greek words for different areas and things like that.
One final thing, and that is whether it is possible that in the future, we could have a material that would be shaped like a wand, in other words, a bit like a stick, and do some really amazing, I guess, either powers of discharge of static electricity or magnetism or lasers that might start to come close to what a magic wand does? Or is the magic wand something that's always perhaps going to be more fantasy than a reality?
I feel like it's always a little bit out of reach, really. Just the scale that you need to do things, to use those forces to actually move things in our everyday experience. It's probably a bit too powerful a magnet that would be required, or a bit too much electrostatic force. But there are, these kind of things that you can do, little tricks and stuff like that. You can have a bit of fun with that.
Well, I'm going to be going home and checking out my 30 centimetre ruler. I'm trying it out on my son and the tap maybe later on.
Yeah, you'll have a lot of fun.
Natalie, thank you so much for joining us.
Thank you.
Thanks for listening to this episode of Sci-Fi Sci-Fact, hosted by me, Brian Crump, produced by Andrew Robertson, and of course, made possible thanks to the incredible knowledge of those brilliant scientists at the MacDiarmid Institute. You can find more episodes of Sci-Fi Sci-Fact on the RNZ podcast page. RNZ podcasts are also available on Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or pretty much wherever you might find your podcasts. And make sure to follow us so you don't miss out on any new episodes.